Okay.
Yes, I'll be back. Okay, see you in a bit. Bye-bye.
Oh, it's just something I should have shared maybe. I don't know if Pravin's gonna be in this meeting, but we've been doing this semester group readings with the research group, and I can maybe send that to Leela and she can spread it to the group. We've been reviewing two review papers of 2024 that talk about different causal inference methods and causal emergence. Um, it took 5 of us and 3 different meetings to like tackle at least maybe the paper. It was very interesting. So maybe I can send those 2 papers to Leela and she can spread them to those. But the one on the causal emergence was really interesting. Yeah, I think I will just share this with Leela so she can propagate through the group. And so of course there is an information theory approach to that. But yeah, it was very interesting. Just a side note. I should share
Cool.
this.
Did you guys record your discussions or no?
No, it was just meetings with Allison, the Praveen Research Group, and some other people that you invite. So we didn't record anything. But I mean, if Praveen agrees that we have the presentations, we have the PPT, we can maybe share.
Sure.
It's like 60 to 65 papers, 60 to 65 pages per paper. There is 2 of them. So and it's dense. So yeah, maybe a summary would help a bit.
Absolutely. I don't think anybody wants to wade through 65 if you could get a summary.
Yeah.
All right, let's give a few more minutes for people to sign in. I got to go check on my cat. It's only 2 past. Okay, let's give them another couple more minutes. Hey, Jonathan, how's things?
Oh, pretty darn good. Yeah. How are you?
Enjoying the beautiful spring weather.
Yeah, it's here in Santa Barbara, it's pretty foggy. Doesn't seem very spring-like, but that's normal.
You have a lot of fog at this time of year?
Yeah. The fog is actually like heavier in the spring and summer.
Interesting. You get an inversion or what happens?
I think just the
Humidity?
the higher pressure allows the air to capture more water.
Hey, Dan, did you hear back from those guys yet?
No, nothing yet. I don't know what to expect as far as what how many emails do authors receive? Not taking people write
I'm
papers.
sure. You never know.
Worth
It's always
trying.
worth a try, right?
Yeah.
Right. Hi, Yang.
Hey, hello.
Is this your building in the background?
Yeah, it's the main building of the university.
Oh, looks very fancy.
Yeah, 100 years old building.
100 years. Built by
Yang,
built during the British
Yeah,
period.
teach occupation. Yeah.
Did you ever give your presentation?
Last year, July. Yeah.
Oh, okay.
There will be a new one in the coming May 1st, I guess.
Okay, cool. I think I missed your one last year, but I'll find the video.
Okay, there will be a new one coming soon.
Great.
Hey, Jasper.
Hi, Ocean. Hi, everyone.
Okay, Luis, I think you can take it away. Are we recording? Yes, okay, I see the recording. Yeah.
Okay, yeah, I think it's okay. Yes. Okay, I begin. Okay, today I'm going to present this kind of part of my research in the PhD, but in some part is about HydroLSTM, this kind of architecture that I have been developing, and how we can use this kind of representation to explore about regionalization. So for this reason, the title is kind of exploring catchment regionalization through HydroLSTM. So from the question that the main question that I have for motivation here is coming from this paper that are kind of the 23 unsolved problems in hydrology. So one of these questions is exactly that, what are the hydrological law at catchment scale and how do they change with the scale? So in some way we are talking indirectly about regionalization, because the idea is how we can know how catchment is going to change when we are, for example, we are changing kind of land cover, or we are using, or we are changing the size or something like that. So how are the relationships that are behind? And for that, I had this kind of question that we know that in some way machine learning is doing very well in this kind of task, especially when we are using this kind of regional model especially for LCM. So the idea is how we can extract this knowledge. So how machine learning can help us to discover this kind of regionalization relationships there. And for that, I don't know, I'm assuming here that everybody knows in some way what is LSTM. So if you don't know, please stop me at any moment. Or you have questions, please stop me, don't worry. But so here I'm going to present what I'm talking here about HydroLSTM. So what I did is, I began from LSTM representation that is kind of a very similar to the idea of the linear reservoir. In some way, we have a state variable, we have some initial conditions, some input, and this way we can do the prediction for the stream flow. And with HydroLSTM, in some way, I'm kind of copying that at the beginning from exactly the same, but I did two main changes there. So the first one is that with LSTM, in some way, when you are training, you are using kind of the sequence length. So you are beginning from, I don't know, from 1 year in the past, beginning from assuming that the state is 0, and then you are kind of updating the state variable each time step until today. So this way you know the state variable today, and you can do the prediction using this state variable. With HydroLSTM, what I did is that I'm just updating the state one time. So I'm just taking the state from yesterday and update it given the input that I have. So in this way, I don't need the kind of begin from some initial condition, assuming that it's 0 in the past. I'm just using the previous time step. And the other change that I did is with LSTM, we have this kind of forcing that we are updating the state each time step using the forcing for this specific time step. But with HydroLSTM, and given that updating only one time, and using this kind of sequence length or this kind of pass information, and adding this directly inside of the gate. So in some way, the gate has the kind of all the past information. So we have, for example, precipitation from today, precipitation from yesterday, and all this kind of lagged data from the past. And this way is kind of learning what is the relationship using this kind of past information. So the idea to create this kind of representation was trying to learn about that, especially about interpretability, to see how much we can, or how much knowledge we can extract from that. So to test that to see how much we can learn, first we did this kind of experiment where we took 10 catchment and we did many analysis just with that. And the 10 catchment are coming from, you can see this map. We have these kind of different regions that are coming from this paper that is uncovering flooding mechanism. So in some way, I took 2 catchment for each one of these regions, and I did a lot of analysis with that. I'm using precipitation and temperature as input, and I'm training 1 model per catchment. I know that this is kind of not a common way or to get the best performance, but here, given that we are focusing on trying to learn or get a more parsimonious representation, we are doing this analysis, training locally, catchment by catchment. So this way we fixed all the hyperparameters, and the only thing that we can in some way change is the number of cells that in some way related with the number of the state variable that we have inside.
Yeah.
And question? No, somebody? No. And the number of lag data that in some way is related with the memory that a catchment has. So jumping to some of the results. For example, here we have a snowmelt dominated catchment. So we did this analysis using 1 cell for LSTM, 1 cell for HydroLSTM, and we explored with different number of cells in parallel. So for the reason we have between 1, 2, 3, 4, and with different kind of sequence length or kind of path memory. And we trained many models, 20 models for each one of these kind of pixels. And here the color is telling you what is the mean KGE. So the first thing that we can see immediately is that the color, kind of the distribution of color, is completely different. So LSTM in general is using more number of cells than HydroLSTM. So in fact, you can see here when we have the red asterisk here that with only 1 cell, we can have almost the same performance like you can have with maybe 8 cells in LSTM. So we are using less number of cells. Why this is important is because this way you have the chance to kind of explore and see what's happening inside of the architecture. That is the idea of the interpretability. So if we have 1 state variable, it's very kind of easy to see what's happening inside. So in some way, what this was nice, we are using less number of cells, but what else? Then we did the kind of analysis about the weight, because remember that we are using the gates are receiving all the forcing at once. So all the precipitation for, I don't know, 1 year in the past, all the potential transpiration for 1 year in the past. And we have 1 weight for each one of them. So if we plot the weights for each one of these forcing, we have this kind of plot. So here in the y-axis, you have the weight, and in the x-axis, you have the day, the time, the lag that you have for this weight. And you will see immediately that the weight that the model is using for the precipitation forcing are higher than what is using for potential transpiration. And in some way, this is telling you that this catchment is in some way precipitation is more important. In some ways, kind of controlling the behavior. And this is interesting because this is exactly the behavior that we have from the previous map that we have here. So in some way, we know what are kind of the mechanisms that is behind. And just the plotting the weight, you can see what is the dominant behavior that is matching exactly what we had before.
And
so
Luis,
in some way, yes, please.
So sorry, can I ask a few questions? Can you go back? I think it's 1 or 2 slides. Yeah, this one.
Yeah.
So number of cells versus time lag. So why? I don't understand all the details, but I would expect that, for instance, with 8 cells, why does the performance get worse if you increase the time lag, or when you go further back in time? Why does the performance get worse?
For which one? For the
Yeah, the
LSTM?
left. Yeah.
In some way, there is kind of a trade-off there, because it's In the case of HydroLSTM, in some way, you can see that you can increase that and you are kind of keeping the same performance. But with LSTM, in general, you are adding more and more and more. So in some way, you are kind of learning different behaviors. But in general, LSTM has this kind of property that you can add more cells and you are getting better. So it's not always that we are getting worse, but there are some specific lag that in some way you are getting worse.
Okay,
So
so
if
are
you
you
using, I don't
talking
know,
this is evaluation period?
this is the testing period.
Testing. So is all the data so what is the loss function you're using?
Mean square error and the period that I'm using, I don't have here, but it's,
Okay, yeah, no,
I train.
okay. So and is the testing using evaluation as well, so that you have a calibration set, right? And then the network
Yes.
also uses evaluation to find the optimum.
Exactly.
So then I still find that strange, because I would expect if you do multiple trials that you ultimately will see that the performance increases if you're in sample. Out of sample, for sure. But in sample, I would expect that when you increase the number of lags, that it continues to improve.
Yeah, this should happen if the architecture is kind of able to learn from more kind of lag data. In general, this is something that is a kind of open question, but from my point of view, with LSTM, that this idea that, okay, in general, all the LSTM model is using kind of 1 year of past, or the sequence length. This doesn't mean that there is not more information in the past. From my point of view, is that really the architecture that we're using is not able to extract this knowledge, because the amount of information that we can get from I don't know, for something that happened more than 1 year in the past is very hard. It's very little, so it's very hard for the model to extract this knowledge. So in some way, you begin to confuse with noise.
So then last question about this. If you evaluate the model using the KG, why don't you train the LSTM based on that objective?
I remember for what experiment I tried it. The problem with KG is that it's not a very good loss function, because you have a ratio in some moment. So in some, depending on when you are doing the backpropagation, in some moment you can be in areas where you can explode the loss, the KG, because you have the ratio between some value and another one. So it's not
Because
a
that's
very,
a
very
question
good.
I asked Hoshin a while ago. It's still my understanding that almost all people using LSTMs, that they calibrate using a regular L2 squared residual loss function, because there you have the Hessian, the Jacobian, have all the derivatives. That's the standard software. And then I understood from Hoshin that that also was derived from for the KG, which I never understood from literature. So that people do actually calibrate those networks by maximizing the KG. But I always wondered that, because that fundamentally changes your Jacobians, your gradient factors, and then the backpropagation. Anyway, so it's calibrated using the R square, or I mean the squared residual, and then you compute the KG. Okay.
Yeah.
Thank you.
We'll have to talk to Yuan, because he's been using KG for network training. So maybe he has some insights into that issue of Luis's.
Okay. Great. Because I like to generalize that theory then further, that people can use any type of scoring rule or scoring function. Go ahead, Luis. Sorry to interrupt.
Yeah, no, don't worry. Please stop me. If not, look like I'm talking alone. So please. Somebody
Luis,
else has a question?
Yeah. Can you go back to your weights map? Can you clarify how you're getting those uncertainty bounds on those?
Yeah. In fact, this first, I'm going to return to this one, because here I have mean KG. So really I'm running, 20 an example, really 20 different models with different initialization. So for this reason, I have this kind of uncertainty there. From this kind of 20 models that I'm running, I know exactly for a specific lag and number of cells, I have different kind of weights. So this way I can see this kind of uncertainty. Somebody else has another question?
Now, about that uncertainty, Luis, is that a 95%? Is that what do we see here?
Yeah, here this is just the kind of the in some ways it should be 75 and 75 and 25 because we have the kind of 50%.
Oh, it's
percentile.
50%. Okay. Let's stay. Okay. Yeah. Okay. Thanks.
Another question? Okay, continue. So here in this figure now, because previously we have this one where we were showing that the weight in some way are informative about what is the hydrological behavior. So this is kind of rainfall dominated. And when we move to another one, kind of snowmelt dominated, now we are changing the importance in some way. So now the weight for potential evapotranspiration that in some way related with energy are more important in this kind of catchment that is a snowmelt dominated. So in some way, the weight that the model is learning are telling you what is kind of the hydrological behavior that is behind. So this was, for us, was very important because this was actually the idea of the change in this kind of architecture that should be more interpretable. Then, because with all this kind of experiment, we tested with kind of 10 catchment, with adult analysis, and then we said, okay, we know that in general, from this figure, we know that with only one cell in general, we can do very well with HydroLSTM, so we can use this number of cells. So we said, okay, we are going to fix that. We are going to use only one cell per catchment, and we are going to train many of them. So then we training more than 500 catchment, and now each one of these catchment is going to have a specific distribution of weight, and you can do the kind of k-mean clustering to define what is the behavior of each one of them. And what we found is that, in fact, that there exist this kind of clusters, and in some way the model is learning something that is different for different catchment. So here is clear, for example, that there are some group of catchment that, for example, the red line, that where potential evapotranspiration weight are more important than the precipitation one. So in some way there are kind of these different behaviors. Or we have another kind of the blue one that are where the weight for yesterday precipitation is very important, and then we have this kind of decay when you are increasing the time. Another one that, for example, the green one, this is interesting because yesterday precipitation is important, and the day before yesterday is important, and then we have this decay, but it's not so steep compared with the other one. So in some way, there is kind of this the idea of memory. In some case, the model is learning that for some catchment, the importance of the past precipitation, maybe 10 days in the past, 5 days in the past, is more important than other ones. So the model is learning that there are different kind of behavior behind.
In a sense,
So-
Luis, when I'm looking at this, I'm thinking this sort of reminds me of, it's like a different attention mechanism. I know it's fixed, but it's like a different attention mechanism in each catchment.
Yeah, in fact, from my point of view, what we are doing with HydroLSTM is a kind of a mix between a attention mechanism and because we have this kind of weight that is fixed for it's kind of a convolution in some way. We have this kind of kernel that is applied for all the time steps. And at the same time, we have a state variable that is kind of storing the Markovian memory. So we have this kind of two behaviors.
The only,
Jonathan, you have a question?
the only difference is it's a fixed attention mechanism as opposed to
Exactly.
a variable.
Yeah, I guess so the motivation is to look for like the general laws across catchments. When you train a single model on many basins, it's learning those general laws, and then it's learning some particular things from the static attributes. So when you train one model on one basin, there's no chance for it to generalize. So I wonder if you did the same thing with a model that was trained on many catchments, would you?
Yes, it's coming.
Okay, cool. Thanks.
Yeah, for the reason first, we did all this parent catchment by catchment just in some way to see that we are able to extract this kind of behavior, that the hydrological behavior. But this is kind of the idea. Go to only one model that is learning this kind of regionalization. Okay, so then we are still here training catchment by catchment. So previously we have this kind of cluster And this is now the distribution of this cluster or training locally. And we see immediately that there are kind of regions that in some way make sense, that we have a red region here where are located in a kind of snowmelt dominated, that the blue one that in general are more related with kind of mountain range regions. So in some way we have more rainfall dominated processes. So in some way the weights are able to capture this kind of different behavior, and in space makes sense. So in this way, in some way we know that probably go to the only one model to create a regional model in some way should be the right direction, because we know that the weight already are telling you something like that.
Luis?
So yes, please.
It's almost like the light blue and the dark blue are, at least from a spatial point of view, don't seem to distinguish much. Can you go back to the clusters? Okay, yeah, they're very similar. All right.
Yes. Yeah, in some Jonathan, question, please.
Oh yeah, can you go back to the cluster map? This is something I've seen in several different clustering mechanisms, is that light green, there's light green is very scattered throughout the east, right? But
Yeah.
then you have at least a couple light green in the Pacific Northwest and into the plains. I've seen that same thing arise from other clustering mechanisms.
Okay, good to know. But in general, in this point, we are still, this cluster are not, how you say, they are kind of some similarity between catchment, but we are not imposing that because we are training locally. So for this reason, then we have to, the idea is more to the other one, exactly that, to have kind of explanation why we have this kind of different behavior.
Yeah, so what's really cool about this is that the other cluster methods I've seen have to do with the attributes of the basin, but this model doesn't have anything to do with the attributes, it's just the response. So
exactly.
Yeah, super cool.
Okay, so given that we know that this in space in some way, there is some relationship with catchment attribute. The idea was exactly that, to explore, okay, are we having this kind of response, or there is kind of some attribute that could be related with that kind of feature that we are finding, this kind of shapes? So we did an experiment, given that we have this kind of more than 500 catchment, and we clustered we separated that for aridity, just to test that. So we have, for example, catchment that we have the aridity is very low. So in some way, it's very wet catchment. And what we found is that in general, this kind of catchment, when you increase the lag data, in general, with kind of 1 month, maybe 2 months of data is good enough. You are getting the best performance for this kind of catchment. Here is the kg, in some ways, a ratio. So how fast we are getting the best performance. So for the reason, the kg divide for the maximum kg that you can get for that catchment. So we can see that this kind of group of catchment, in some way, the lag information not so important. But for arid catchment, we see that this change is completely different. It's very sensitive to that. So we need to increase a lot of memory to get the best performance possible. In fact, in this experiment, when we tested that, we used just 256 days, and look like really we need more than that. So, but at least doing this experiment, we can see that there is kind of relationship in kind of the shape or the behavior that the model needs or is learning versus some kind of catchment attributes. So for the reason then we moved exactly to that. Okay, can we predict this kind of weight? Yes.
Sorry, what was the distribution over? What are you distributing over? Which set of catchments?
What do you mean?
You just did 2 categories, wet and arid, or you're doing your clusters 1, 2, 3, 4, 5?
In fact, this kind of another class, because we are kind of arid and no arid catchment.
This
they're
is
not
the
related.
index. Okay.
Yes, but it's not related with the classes that we have before. In some way, we took the entire group and we separated just for kind of aridity. Yes. So the idea was exactly that one, trying to And this is the part that we are moving to this kind of regionalization where we are learning only kind of one model for all the catchment. And here is when I'm beginning. This is kind of all the results that I'm going to present now are kind of preliminary results because all the previous ones are related with the paper that I already published. So this is kind of the second chapter of my PhD. And the hypothesis is like that we should be able to find that catchment attribute define the dynamic through the shape of the wave. So how we can learn this kind of relationship where we have kind of catchment attribute and we can predict what is the shape or this kind of distribution of the weights. And for that, what we are doing, we are taking kind of different catchment attributes. We have topography, climatology, land cover, soil, geology. We are not adding any kind of catchment attribute related with the kind of hydrological signature because this is exactly what we want to learn. So we are not adding nothing about that. And we are using random forest to learn that. So random forest is going to take all the catchment attributes and it's going to predict what is the distribution of the weights. This is the idea. And why we are using random forest? Because in some way, random forest is using explicitly this kind of cluster. It's splitting the space given the catchment attribute, and it's using this kind of different regions to predict the distribution or the distribution of the weight. So in some way, we are very clear that, okay, we have this kind of region, this kind of cluster, and using random forest is kind of very easy to explore what's happening inside too. So this way we can get kind of interpretability inside of the regionalization process. So what I'm doing here with this idea of the regional HydroLSTM now is that we are going to continue with this idea of training locally. So we are training each catchment locally for some number of epochs. So in some way, each catchment is trying to learn the best weight possible. But then after some number of epochs, we are going to impose this kind of a random forest model that is going to learn the regionalization. So in some way, what we are doing is that HydroLSTM is trying to get the best weight possible, but random forest is going to tell the model, okay, wait, if this catchment has kind of similar catchment attribute, they should have similar weights. So we are adding this kind of extra step where in some way we are imposing this kind of constraint. So for the reason HydroLSTM is receiving just the dynamic forcing, and random forest is receiving just catchment attributes, and random forest is trying to predict the weights. So we are doing this kind of in a sequential way until we get kind of the best random forest model.
Okay, this is something I hadn't understood before. So the catchments are not using the same pattern. They're using actually the exact same weights. Every catchment in a cluster is using exactly the same weights.
Yes.
Okay.
Because the idea is that behind that the weight in some way are kind of they are encoding the dynamic of the catchment.
Understood.
So for the reason, this is the idea.
But you're essentially requiring every catchment to have exactly the same structure.
Or at least similar, similar enough, yeah.
Well, if the weights are identical, then it's exactly the same, right?
Yeah, but we are never going to have exactly the same kind of catchment attribute. So we are slightly different catchment attribute between catchments.
So slightly different catchment attributes give you slightly different weights, or slightly different attributes cluster into one cluster with a fixed set of weights?
No, it's not fixed. So we are, because the model is using just catchment attribute to predict the weight. So in some way, we are going to have one-to-one.
Okay, I see. Okay, go ahead.
Of course, they are going to be similar if they are in the same cluster, but they are not going to be the same. I saw a question.
Yeah.
John? Yeah.
Okay, so I think you can do another way around, which is to predict the catchment attributes using the weights to see whether the weights contain like sufficient information to, I mean, which information is used to construct the weight. So we can do the other way, like reversely, to predict the attribute using the weight. You can see like 100% the catchment area is captured by the weights, for example. I think it's a good direction to try. Yeah.
Yeah. It's a cool idea. Yeah, it's true. Yeah. I like it.
Yeah.
another question in the chat. Manuel.
He just said he had to leave. Yeah.
Okay. Okay, so I continue. Okay, so some preliminary result here. So given that we are using random forest here for the regionalization, and this model is learning just this kind of step, we can dig inside to see what was important in the regionalization process. So this is kind of the feature important that we can extract from random forest. And we see here that elevation in some way was very important. That in some way, if we return to the map that we had before, maybe this one, in some way it makes sense because the model we see here immediately that these kind of red regions are exactly with area where we high elevation. So the model learning that split the space in kind of high elevation, low elevation was important. So it's exactly what it's learning. So here I have a question to share with because I have some feeling about that. So what is your feeling about a model that uses mean elevation as the most important attribute? This is kind of a question I have for the group that is here. So I'm going to tell my point of view. So you can be think completely different than me. This is the point here. I want to discuss with you what is your opinion. Because from my point of view, elevation is just something that is telling the location of something. It's the same like latitude and longitude. That this is kind of another dimension, that's all. So really it's not the main driver of what is the dynamic of a catchment. Of course, it's very correlated, but it's not the driver. So because probably given the map that we saw before, then what the model needs in some way is kind of the mean temperature in the catchment. Because we know that mean temperature is very correlated with elevation, but if we don't have this kind of catchment attribute, in some way, it's kind of picking elevation because in some way it's very correlated with the other one, but really it's not the driver.
Also pressure and humidity.
Yeah, many atmospheric variables are correlated with elevation, but from my point of view, it's not the driver, and this could be dangerous in some cases, because especially when we are, for example, using this kind of model for climate change, where we know that we are changing this kind of the mean properties, mean attribute in a catchment. If we have a model that is kind of tied to this idea that elevation is the most important, elevation is not going to change with climate change. So in some way, we are going to be losing this kind of sensitivity. So we have to be careful about this kind of catchment attribute, or at least this is my point of view. So please, if somebody has another opinion, I would like to hear that. So I don't know if somebody has an opinion about that, please. I'm using you guys like a guinea pig here because this is part of my next paper. So if you have any opinion, please.
So Luis, can I ask you, so mean elevation as your most important attribute. So what is the model supposed to do? Forecast snow depth or?
In some way now the random forest is just learning the different regions, or what is it's learning different dynamics in some way, because it's predicting the weight that go inside of the HydroLSTM. So it's learning what is the different dynamic inside of in some way US. It's using catchment attribute to define what is the dynamic in the catchment.
Okay, and the LSTM the goal was they are trained to describe the discharge response.
Yes.
Okay, so we use mean elevation as an accurate predictor, hopefully, of the weight that goes into the network that predicts the discharge response.
Yes.
So, yeah, I sometimes have discussions with my colleagues. I mean, it all depends. In climate, you have these teleconnections, and some people find when they do data mining, they find relationships between precipitation in one place of the world and then precipitation half a year later in another place of the world. And they use historic data. It's a strong connection. They don't know why. There's no physical explanation. And climate people don't like that because they say you need to have a physical cause-effect relationship so as to why, say, precipitation in eastern Russia would cause enhanced precipitation in southwest of the US. They want a physical, like a teleconnection, right? So whereas I tell my students, if you can predict the rainfall in Southern California ahead of time with the number of bikes in New York, who cares, right? I mean, if you're only interested in a good prediction, so here, this question is hard to answer. I mean, if you care in getting good predictions, if you care in understanding so as to why you get those good predictions, that's a different question. But I would say if mean elevation is an attribute that seems important for the prediction of discharge, then yeah, okay.
Coaching?
Yeah, let me reframe the question slightly differently. Every catchment has some dynamical pattern of response. You feed it an input, it delays, it partitions, whatever the processes are inside a catchment to distinguish the impulse response of the input-output response of the catchment. And then the question we're asking as hydrologists is, what is controlling that input-output response? And we're assuming that it has things like geology, soil type, vegetation, topography, slope distributions, network connectivity, and so on. This is what we've been studying for a long time, right? And but we don't always measure all of those attributes. So I don't think the camel set, for example, includes maybe it does information about stream order, connectivity, distribution, stuff like that. Yeah. And then the question then becomes, let's say you knew what all those things were. What kind of attributes could you think of that would be predictors of those things? What attribute would predict geology? What attribute would predict soil type? What attribute would predict network dendritic formation, vegetation type, slope distribution, and so on? And presumably that's some combination of pre-existing geology, you know, the movement of the plates and so on, the uplift and so on, the sedimentation, all of that, and the weathering of that system due to the climatic effects, right? So you could sort of pull it back in sort of several stages. And I was discussing this with Luis the other day, and you know, I was sort of suggesting that one of the most obvious things for me, if I was being dropped out of a plane in a particular place, one of the most obvious things for me would be what is the solar zenith angle at a particular time of year? What would be the elevation? And how far am I from the oceans, as an example, plus maybe something about rock type. Because presumably those are some of the factors that would lead to a catchment having a particular distribution of vegetation, right? How far you are from the ocean determines how much water reaches there. It's obviously much more complicated than that. Anyway, I'm trying to take Luis's question and frame it around slightly differently, because we measure these attributes, but what are they actually informative of, right?
Yeah. Okay.
Dan?
Yeah.
Yeah, I guess like obviously in this figure, the elevation is very striking. Did anything else strike you on kind of opposite end of the spectrum? What you might have expected would be important features that weren't? I'm looking at area. You know, going back to your original question about kind of looking at scaling, right? In some ways. So did anything strike you as surprising that it wasn't more influential or important?
No, to me, not too much, because, for example, in fact, if you go to the other extreme, you can see that, for example, the geology permeability is an, I don't know, carbonate fraction in the catchment in some way has kind of the lowest one. So in some way, the model is capturing what should be, or at least because, for example, we have another group that is kind of related with vegetation. So we have, I don't know, leaf area index, we have a greenness vegetation fraction. So in some way, there are all the factors that in some way we know that, okay, vegetation is important, elevation is important, the slope is going to be important, are there. And area, in some way, given that we are working with, in some way, already kind of a dimensional stream flow, because we are kind of using the stream flow divide by area in some way. So we are already kind of taking off this kind of the importance of this attribute. So we are working in kind of a space that is adimensional in terms of the area. So at least area, for my point of view, makes sense that, okay, it's not the most important because it's adimensional to that.
Thank you.
Jasper?
Yeah, I had a just a thought. So is it possible that you find that the mean elevation is an important predictor because it's actually not used in your LSTM, LSTSM? Is that possible? So in other words, a number of these attributes that are not in the model used as information, right, as inputs, but turn out to really modulate, govern, control the precipitation discharge response, but they're not in there. Is it then possible that after the fact they're found to control? Because this is something you could actually verify if you had a model in which those, you can do this with synthetic data, right? If you had a model and you take mean elevation as an attribute, say, or some other attribute, you generate synthetic data, then you run an LSTM, you do this a number of times, and then see if the elevation then still comes out as an important attribute, or whether it no longer comes out because the model actually accounts for it.
Yes. Well, at least from the point of view of the random forest that we're using here, I'm pretty sure that elevation, in fact, is the first split. So the model each time that is trying to define this kind of different regions is using exactly that elevation to split the space. So we have, in some way, it's related with the map that we have before. So the model is learning that, okay, this high elevation region, low elevation region. And after that, this kind of elevation disappear and emerge the other one. So in some way, elevation for the reason is using, the model is using elevation to separate different behaviors, different dynamics. But after that, really, they are not controlling the dynamic.
No, but if elevation wasn't, basically the way I look at that is that elevation is important in controls the rainfall discharge response. Right?
Yes.
But it's not included in your model as an input. So wouldn't this suggest that we actually should use that as a variable in our models? Is that actually what this analysis is telling us?
Yeah, in fact, this could be a good experiment because I can drop this variable, and it's very probable is that another attribute that kind of related with that or correlated in some way, probably related with vegetation, they are going to emerge like very more important, because this is the problem with elevation, especially because it's very correlated with many other ones. So all the vegetation is related with elevation. A slope is very correlated with elevation. So if I drop that, the other one is going. They are going to emerge.
No, I understand.
Yeah.
I understand, but I think this tells us that elevation is a variable that controls that relationship between rainfall and discharge, but in a lot of the models that is not explicitly taken into consideration, right? Certainly not in conceptual hydrological models, right?
Not directly, it's true.
So
I think it's used in the Snow 17 model. Yuan can probably, Yuan, does Snow 17 use elevation?
Yes.
So some snow models, I guess, use it. Yeah.
But not because you have rain-fed catchments here as well, right? That are purely rainfall.
In some way, we have a huge huge group of catchments, so we have a group of all of them. So yeah.
Yeah. So, but I agree with Hoshin's analogy that if you're dropped off somewhere, just in general, your survivability in nature, you would want to know your elevation because that controls climate, it controls so many variables. So and we don't use it in the rainfall discharge response. And maybe, yeah, anyway, food for thought. And that's the nice thing about this work you do and other people do is that we get these results and they let us think, rethink.
I think Hongli had a question, and then Jonathan. Yeah.
Oh, hi everyone. Can you hear me?
Yes.
Yes.
Yes, I just want to add two factors that from our experience. I remember when I did my postdoc at NCAR with Andy Wood, we found two other factors that may play a very important role in hydrologic modeling. One is radiation. Okay, so radiation, the daily radiation, we calculate based on the of course elevation, slope aspect, and latitude. That echoes very nicely echoed just Hoshin mentions the angle of your solar radiation and another and your location, of course. And another factor we also find impactful is the wind direction. Yes, that one how we test that, we just add those factors in our modeling into specifically the spatial discretization, the way we produce hydrologic response units. And then by giving those spatial discretization configuration, the model gives better simulation results without doing any calibration. So I just found that very interesting. Like you guys already discussed that, and then we also found that from some experiments. So it's worth adding those two factors here.
Very cool. Thank you.
Yeah.
Jonathan and Leela. Yeah.
Yeah. So I've been thinking about this quite a bit too, and so I agree with everything Jasper said, but they were also talking about the collinearity between some of these attributes. And so I did some tests with some students over the summer about like what we did is we did a PCA reduction on all of the attributes that are in HydroAtlas. There's 200 of them. Then we started adding them in one by one. You get to 10 attributes from the PCA reduction, and that's the best performance you get. Just 10 attributes. So those are all, that's the most explanation of variance you need for that. You get like 90% of the explanation of variance of all of these at every attribute you could think of. You only need 10. But then what we did was we just started pulling random 10 attributes without any analysis on them and sticking them in there. And we got the similar performance with just any 10 random attributes than we did with the PCA reduction 10 attributes. So I think that elevation obviously is something that controls these responses, but there's so much collinearity between elevation and like leaf area index, for instance, and all these other things that the model is going to figure out where it is just based on any 10 random attributes. So a smart person that's dropped off in the middle of nowhere doesn't necessarily need to know elevation if he can, or they can see the, some other characteristics of the landscape.
Just a brief comment on that, Jonathan. Since we're an information theory group, we should use the word mutual information.
It's true. Leila?
Yes. Hi, Luis.
Hi.
Thank you. Thank you for this presentation. And my comment is actually elevation seems to be a very simple and elegant way of capturing the local climate. But I wonder if the feature importance will change if you change the regionalization sample. So for example, it's your model trains in catchments where you are near the equator. Then I will say, yes, elevation is gonna be important because like if I go to Colombia and I am in a higher latitude, the climate is gonna be so much different than if I am near the coast, right? But then if you are only training in the plains where elevation is so similar, then your catchments might show very similar elevation, then your model probably elevation is not the main feature anymore. So is the sample training what it's leading to elevation be a very good indicator?
In some way, my guess is that yes, this is exactly what's happening. Is that because elevation is given that it's kind of super variable, or there are so much mutual information with other ones, it's using that because it's kind of the easiest one, but doesn't mean it's the driver. So the same as you said, if you are in the plane and you're training a model with all these kind of catchment, probably elevation is not going to appear there, because really what we have here is that elevation is generally used to split between kind of high elevation, low elevation, because the model is trying to learn something that is snowmelt dominated and something that is rainfall dominated. But if you are inside of the rainfall dominated, probably elevation is not going to be important or not much in some way.
Right.
So in some way, yes. In some way, the features that we're finding in some way are that influenced by the data set that we have.
Mm-hmm.
Going back to Jonathan's point, Jonathan, you found 10 attributes, but you said any 10 attributes almost, not necessarily any 10. I'm sure you could find 10 bad ones, but randomly you could choose 10 and they would work. So that sort of interestingly begs the question as to what constitute the 10 dimensions of things that dominate the physics of what's going on, right? Understanding that you could rotate these in any way you want and get all kinds of combinations. But if they were independent, what would they be? That's, in a sense, that's really the holy grail of regionalization by attribute.
Exactly.
Yeah.
Hi. So I was thinking of like explaining the overall behavior of the model and versus explaining the model's behavior for single catchment. There are actually some methods can work can explain the model behavior for a single catchment. It's called like local explanation method. For example, like SHARP. I think this one, those kind of method may be useful for understanding a particular catchment. So this is a response to a Leila's question as well, for understanding the behavior for catchment in different regions. So I will send the paper link into the chat, so you can take a look about the local method for explanation of the model behavior. Thank you.
While you're there, Yang, would you think about taking these 100 attributes that Jonathan talked about, whatever they were, and doing a latent space projection to try to find a 10-dimensional latent space where the individual latent vectors are independent, which is the underlying latent vector model that would generate those 100 attributes that he's talking about.
Yeah, I think that's a very interesting idea. So in my latent vector model, so I actually separate the representation between, there's a distinction between models and catchments. So for here, we are actually learning the model weights. So they are not actually representing a catchment. So there's some distance between a catchment and a model. Because for a catchment, the observation we take contain many errors or uncertainties. And for a model, everything is certain. It's like it's a set of numerical equations. And we cannot assume that the model actually represents a catchment. This is my own opinion. So I always separate model representation with catchment representation. If I'm going to build a latent, if I going to find a latent representation of a model, I think it may be useful. It may be useful for using like hundreds of catchment attributes, but it only tells the distance between a model and the catchment is not actually predicting the catchments. We are, for example, if a catchment corresponding to a point in space, our models are some nearby points. We are trying to using the properties of the catchment to predict the nearby points. So there's a mismatch between the goal actually.
Yeah, but Jonathan, correct me if I misunderstood you. I think what Jonathan did was he took 10 random attributes and then they trained the model with those 10 random attributes. And then they took 10 other random attributes and then they trained the model with those random attributes. And they did that many times. And every time they got more or less the same performance. Right.
That's right. And the biggest surprise is that the performance was just as good as the 10 the first 10 principal components of the large set.
So the difference here, Yang, is that the model structure is being, and the model structure is the same. You're just relearning another rotation in the space or something of the machine learning model. But if that's true, then in principle, you should be able to find 10 relatively orthogonal directions, which would be represented by some latent vector. That's kind of what I was suggesting.
Yeah, that's true. Yeah, so actually, there's one paper that they also use random vectors to represent to do a regionalization LSTM training, which published like 2 years ago in WR. So I think the result they got was because the random vectors serve as the same role as the identifiers, like just as catchment identifiers. So they map the catchment identifiers into some meaningful points in a latent space. Then the meaningful points in the latent space can decode into a useful model for prediction. So this is one assumption, but has to be verified further.
Dan. Did you still have your question, Dan?
Yeah, sorry, I forgot to unmute. That's really interesting. So when you say randomized, I think, Jonathan, you meant just a random sample of attributes was selected, correct?
We pulled just any 10 random.
Okay,
we
but the values themselves were not random. They were actually the values that were captured.
Sorry, that's right. The values were real attribute values. The attributes themselves were chosen randomly.
And then Yang, am I correct to what you were just saying is that just providing a unique set of attributes like those you're talking the paper that you're referring to actually randomize the values?
Yeah, the values are also random. Yeah.
Okay. Yeah. Would you mind? Do you have I
will send the paper to
reference? Yeah, that'd be great because someone in our group has also been doing that and finding the same thing. So thank you.
Okay. We'll send later.
Okay, that was a long, that was very interesting, Luis, but keep going.
Yeah, well, at least this was the idea of the discussion. So, okay.
No, this was the important part of this. Yeah, this is where the discovery is happening.
Yeah. Okay. This way. So remember that at the beginning I had this question of trying to find this kind of relationship. So how do the relationship look now? Because we have a model that is random forest model that is kind of learning this kind of relationship. So here I have kind of some of the result. So here I have the feature importance remember that we have one weight for each one of the forcing, in that case, precipitation. So at the top, we have the weight that the model is learning, or in some way, the feature important just for this weight, that is the weight for the precipitation, for today's precipitation. So if we are doing kind of feature important of that, we are now finding that the mean precipitation is the highest, has the highest importance there. That is different than when you're taking the feature important for another weight. For example, here yesterday for potential evapotranspiration. So the feature important is different. And in some way, this is good because it's exactly what we want, that the model is learning different weight in some way that are encoding different hydrological behavior. So the model is learning that some attributes are more important for something and others are important for something else. And the other thing that was interesting here is that, okay, when I found that in some way the mean precipitation was important, I plot this kind of the partial dependent plot, and we found this kind of positive trend. And then I said, okay, in some way, what the model is learning, given that it's a weight that go inside the gate, that is weight time the precipitation. When you have a higher weight, in some way, the model is going to have a strong response in the stream flow. So in some way, this concept of this weight, what it's trying to learn is something related with the flashiness in the catchment. Because if we have a very high weight, in some way, the response is going to be higher. So then I said, okay, I want to check what is the relationship that at least the literature is telling us about what is the relationship between flashiness and the mean precipitation. And the literature said exactly that when you increase the mean precipitation in the catchment, the flashiness in the catchment increased too. So in some way, the random forest model was able to capture exactly this kind of relationship that we know. Then I did the same with the potential evapotranspiration weight. So for that, now elevation is very important. That in some way makes sense because when we change the elevation, we are going to be changing the potential evapotranspiration. So there is kind of something that are correlated. And I did the same experiment. I said, okay, what is the trend that we should find in the literature? And we found that this should be kind of negative. When you increase the mean elevation, the importance of the potential evapotranspiration decrease in the stream flow prediction. So the trend that we are finding here in the random forest model in some way match what we know. So at least this was interesting to me.
Do we see each of these lines as a different catchment?
Yes. Yeah, in some way what we are doing, we are taking one catchment and we are changing just the kind of this case, for example, elevation. So what's happening with this catchment, when you increase elevation, you will see that the response is different. In some way, the weight is different. So then the next step was, okay, we know that the model random forest is learning this kind of relationship, but how they look in the map? Because a random forest has this option that, okay, especially if you take only one tree, you can kind of cut the tree at different level, and you will have different group of catchments. So I did this experiment with kind of cutting the decision tree in the level number 4. And these are the clusters that I found, or this kind of the group of catchment that I found. And immediately we can see that, for example, the cluster number 8 and 9 are exactly in a region where we have high elevation. We found that the number 5, for example, is in a region where in some ways they are more kind of rainfall dominated. The same like 7 and 6. And we found the cluster 0 that is in a way more in the plains. Cluster 1, for example, is in Florida. So we know that the behavior there is completely different than the other ones. So in some way, the model was able to recognize exactly that, different hydrological response or dynamic, that they are kind of different regions. And the other thing that was interesting to me about that is that in general, these clusters are kind of slightly different from what somebody else or you can find in the literature, because you can create this kind of cluster just using just the attributes, catchment attribute, and you will find catchment that are similar. But this doesn't mean that are going to have similar or different response in the stream flow. So you can do this if you are doing just in the input space, that's catchment attribute, you can find this kind of cluster. You can do the same using just kind of feature that you can extract from this stream flow values. So you can define different features, you can find similarities, and you can find clusters. But these clusters are hydrological clusters because what we are learning here is the catchment attribute that are correlated with the stream flow. So it's kind of this idea of kind of latent space, or the group of catchment that has similar catchment attribute, but at the same time they have similar dynamic.
Where did you cut the tree to get these clusters?
In the level 4. So I
Okay.
took the best tree in some way because, okay, we have a random forest, so we have many trees. But I took just the best one to see what is this kind of region.
So that's 4 yes/no questions?
Yes, but in some cases, the decision tree can kind of finish before than the other one. So it doesn't mean that we're going to have all of them.
Maximum 4 questions, yeah. So basically 4 cuts in the features, in the attribute space. Interesting. And the cuts were on 4 different attributes, or some attributes are repeated?
Some of them are repeated, it's true.
It would be nice to see that tree so we can see which
I
are the
have it at the end.
Okay. All right.
Even we can watch it now, but I have to,
Yeah.
to finish.
Right.
So something that is interesting about this kind of cluster, for example, cluster number 5, we can see that the weight that the model is learning for this kind of region in general has the highest value compared with all the other ones. And this cluster in some way is a region where we know that it's kind of rainfall dominated, and it's very steep because in some way we have mountains. So in some way it's related with this idea again with the flashiness. So the model is learning exactly that behavior. Another kind of group here, we can see cluster 6 and 7 that are in another kind of mountain region. But in some way, from the hydrological point of view, we should find that this cluster should be kind of similar because the response should be this way, at least what we know. And the model created this kind of cluster, but you can see that the different weights here, I have today precipitation weight, yesterday, and many of them, or well, at least some of them. And you will see that the values are kind of similar too. So the model is creating this splitting, but probably in a kind of upper level, they are in the same cluster because the response is very similar. So that is nice too. The other thing that we found here is that cluster 8 and 9, that they are in kind of snowmelt dominated regions, we have the higher value for the weight that is learning for 10 days in the past precipitation. So in some way, the model is telling us that it needs a lot of precipitation in the past. So for this reason, it's using a higher value of the weight compared with the other ones. All the other ones you have lower or even negative or 0 in some ways. But this 3 in some way has the highest one. So in some way, we can see that the model is learning exactly that, this idea that, okay, some catchment need more memory and is storing this kind of memory in this kind of in the weight in some way. This is coding exactly that behavior using the weights. Okay, so now I'm going to jump to something. Leila, you have a question.
Yes, Liz. When you are training your model for regionalization, you mentioned that, okay, you didn't include, you only include like latent variables, variables that doesn't change with the climate. At what spatial scale did you are your inputs? Did you use satellite information to, or is just one data point for each of the catchments?
Yeah, I didn't mention that. I forgot that. I'm using Camels dataset. So in some way, it's already set there. I didn't add any other one. So it's just Camel dataset. So we have this kind of catchment attributes that are already defined there. And the forces are defined too, that are coming for some of them for reanalysis and there are many of them.
I see. Okay. Thank you.
Okay, so remember that at the beginning I said that this, or at least HydroLSTM has this chance that you can learn only, in general, with only one state variable, you can learn a lot. So all this kind of experiment, all this kind of regional model that I'm training here was learning only one state variable per catchment. So that is nice because now we can go and see what the model is learning or what is inside of this state variable. And this is one of them. So this is kind of a snowmelt dominated catchment. And I remember the first time that I saw that, I was kind of shocked. What? Because here you can see that the red line is the state variable. The kind of green is the stream flow, the prediction that we are doing. Dots are observation, and the top we have precipitation and the mean temperature in the catchment. So my idea when I was creating this plot was find something like SUI, because we know that this is important in a snowmelt catchment. But we didn't find that. What we found is that the state variable is kind of flat, exactly in the winter, but then it's increasing in the summer. This is kind of exactly the opposite that I was waiting for. And then I saw that really this area is kind of flat, but really the state variable is matching very kind of the rising part of the hydrograph. So this was okay, this is weird. But here, do you see, we have another one. This is a now kind of rainfall dominated catchment. And you will see that the state variable, the red line, is matching very well, at least the prediction that we are doing, that the other one. Except in some cases, especially here, we have kind of precipitation. And the model is learning that when you have precipitation, you have to, in some way, increase the value of the state variable, or what the value that you have in the state variable. So when I saw this kind of figure, my guess is that in some way the state variable is learning something like what should be the stream flow in the river without context. So in the case of the rainfall dominated, probably is learning something like what is the flow that should I have if I don't have precipitation? That is the driver, the main driver there. And in the case of a snowmelt dominated, given that the main driver is temperature, what is learning is what should be the stream flow in the river if we have enough snow. So the model is learning something that is storing information and something that is contextual information. So in that case, probably the forget gate is doing exactly this job, that probably is kind of correcting the value that we have in the state variable. And in that case, the snow, when you have probably snow in the catchment, okay, you are matching that both behavior. In some way, the prediction is very correlated, it's almost the same like the state variable, but then in some moment you are uncoupled that, because in some way you are using all the snow. So the model is probably learning exactly that. The gate is learning, okay, you are using all the snow that you have, so you cannot generate so much stream flow. So it's correcting that. Or at least this is my interpretation about what is learning here. So I would like to hear from you guys, what is your opinion? What do you think the model is learning? Because in this moment, I'm just speculating about this kind of relationship. So if you have something different, some different opinion, I would like to hear that, please.
So the top one, explain the top one again. The top one is a snowmelt dominated catchment?
Yes. So given that this, or at least from the hydrological point of view, the main storage should be SUI, the snow that we have in the catchment. But the maximum should be kind of in March, something like that. We should have kind of responding the winter. And really the model is kind of flat. It's not learning nothing like that. Or at least there is the information that is in the state value. And in fact, the state value is very high in summer. So it's something different. So for the reason I think that what is storing in the state variable is something different than SUI.
So this is the variable that is being multiplied by the gate.
Exactly.
Generate. Maybe you should plot the gate variable also.
Yes, yeah, for sure. But at least we can see that when the state is the same like the prediction, probably the gate is close to 1 in some way.
So the state is somehow, in the top one, is somehow tracking temperature, yeah?
Yes. So for the reason, I have the feeling that in some way the forget gate is doing something like it's storing kind of the context, and as for a snowman dominated, the concept is mainly the snow that you have. So you have snow or you don't have snow. That is changing completely the mechanism of the forget gate, but the output gate. So.
But if you look at the section from 2004-5 to 2004-6 or so, it seems like the gate would be wide open, right? And then when it gets to the peak, somehow the gate then shuts down. And it has to go close to, it has to drop off to 0 in order to generate that stream flow. Does that make sense?
Yes.
And because it drops off to 0, then whatever is going in, whatever it's then storing is storing something, but it can't release it. Yeah. It's
Exactly.
storing some information, but it can't release that in the form of stream flow. Interesting.
So why I'm asking that? Because in some way, I have the feeling that the state variable, given that, because in some way, remember we have the equation that is stream flow equal to the output gate times the state variable. So what is trying to learn the model is trying to maximize the mutual information between the stream flow and the state variable, something like that. And the forget gate in some way is kind of adding this kind of correction that is given the context. And this idea in some ways very similar to the idea maybe to the base flow in a catchment, because this is the flow that you have in a catchment in a river if you don't have precipitation. So for the reason, when you don't have context, probably the scenario is something similar to the base flow, something like that.
Let me ask a devil's advocate question here, Luis. If you were to actually plot the gate, okay, it would have something like the behavior that I just mentioned, which is, what if you reversed the interpretation that the gate is actually tracking something like the soil moisture state of the system, and the state, the informational state here, is actually tracking something like the gate?
Yeah,
because it's multiplying the two together, right?
Exactly. It's possible. It's true. Yeah.
And so somehow the interpretations are getting reversed here because you're only looking at one of them, right?
Yes, it's true.
I think we absolutely need to plot that and see what's going on.
Yes. My guess is that that is true. In fact, because I did some experiment that in general, you can switch between one another, but the model is more kind of, it's more probably that the behavior is always this one. Because the first time I remember when I was doing an experiment, I was trying to kind of push to the state to learn something like sweet. But the model was always moving for something like, okay, the highest value is in summer. It was kind of weird. So probably for the model, it's easier to kind of separate to kind of store that information in the variable this way, and the other one in the gate. But it's true that the other cases we can kind of switch between one another, but probably it's less probable, harder to learn at least.
This almost suggests, if I compare this to the work that Yuan did, it's almost like your red thing is tracking a loss gate. Right? It's tracking information about evapotranspirative loss, because it's highest when the temperature is highest. It's like a potential loss term or something.
Yeah, in some way, for the reason I said, it's kind of the stream flow that if you have enough kind of sweet in the catchment, this is how much you are going to generate given some temperature. So if you increase temperature, you are going to begin to increase the stream flow if you have enough sweet.
But I'm suggesting it's almost like it's evapotranspiration.
Could be here in some way we are not imposing any kind of constraint in the state, so it's true. In some way we are kind of guessing what is learning the model, but at least it's only one. This is what's interesting for that we can dig inside.
Very cool.
Yes, because for the stream flow, was kind of surprising that the state was tracking in some way the precipitation event, but the forget gate in some way is telling the model that, okay, no, you have to produce kind of more stream flow than what you have in the state. So for the reason I have this idea, it's kind of a correcture factor in some way, or maybe it's kind of related with this idea of the base flow, because then we know that you have base flow in the river, and then you have to add kind of the runoff. That is the runoff is coming because we have some precipitation. So this is going to be maybe kind of the context that we have there. But I said this is kind of a very open question, because really something we're just exploring.
So the blue line is obeying a Markovian dynamic.
Yes.
Whereas the red line is obeying an attention mechanism of some kind. Because the gate depends only on the on the past inputs that have been fed in, right? So the red line is learning a context, basically, some kind of context variable, and the blue line is learning.
I know, but this is in the other case, because red is the state variable. So this in some way is the Markovian.
Oh, I'm sorry, you're right. Red is the state variable. Red is learning a Markovian thing, and we don't have the gate. Because we don't have the gate. The gate is learning the attention mechanism, and that's what's resulting in the blue when you multiply the two together.
Yes.
Yeah, no, we absolutely have to look at the gate. Very cool. But this brings back the question to in LSTMs, when you're tracking states and gates, what are they actually? What information are they actually? In a traditional LSTM, what information are they actually keeping track of? Yeah. And I mean, Freddie showed that at least in some cases, you could show that the cell state was tracking snow accumulation or something. But you also get negative values, right? When you do a standard LSTM, you can get state variables that are
negative. Yeah. And especially because you have so many of them, so many state variables that you can find that some of them are correlated with SUI, but that other one, there could be anything. It's really hard to know.
Johan, it would be interesting to run your model on the same data set and generate the states and the gates, the loss gate and the output gate, and then plot those against Luis's things to see what they're learning differently. Thanks, Jonathan.
Okay. I'm going to, with that, this is the last slide. So from all this kind of experiment, the take-home message that I have is that, okay, we know that the weights in a single HydroLSTM model encode kind of the hydrological behavior. We saw that across the presentation. And the weight pattern follow kind of hydrological regions, because at least makes sense what they are learning, they're coding something. The regionalization model was able to track this kind of sensitivity, so we are getting, or at least from when we are comparing with the literature, so we have the same trends. And this is the part that we were just discussing that apparently the state values, from my point of view, is kind of maximizing the mutual information with the output, and the gate is applying the kind of correction given the context. But this is something that we have to explore more. And with that, I finish at least my presentation. So, any other comment, question? Leila?
Hi, I am wondering if using other sources of data rather than camels will show similar results, or what are your ideas about that?
My guess is that probably the weights are going to be different. but the pattern should be the same because really we are using precipitation and potential evapotranspiration. So we are using, these are the two forces, and these are very generic in some way. So you can change the source of that, taking a satellite product or whatever. But in general, if they are
Precipitation
the
and
same variable,
temperature.
should be.
Precipitation and temperature.
Yeah. And we are using temperature, but really inside of the model, we are using the potential of transpiration. So we are doing a transformation there.
Oh.
We are compressing the information.
Thank you, Luis.
Dan.
Done?
Yeah, that was awesome. Thank you. I guess I have kind of a practical question. So, given the latter half of your presentation, you focused on, like the lag 1, and then you included the lag 10. So, from the beginning where you went up to 256, I take it that was more like a practical kind of processing time or computation limitation, or would you consider exploring, like, would you have considered longer lags or tokenizing the time steps differently if instead of like every day kind of compressing that into shorter
yeah, it's true.
context?
I remember in some moment we have this discussion with coaching that we should be doing something like that. For now, the experiment and the first part of the presentation, I was using just 256 days. And then the second part where I'm doing the regional, I expanded that to 526 catchment. Sorry, lag. And generally, what we found is that exactly that there are some catchment that need more lag than other ones. And even now that, especially when we're training with 500, some of them, they are using, I don't know, I'm going to guess, probably the 10% of these catchment are using 500. So that's mean that probably if I increase a little more, we are going to get a little more performance. Not all of them, but there are a group that they're having this behavior for sure.
Okay. Yeah, and as I recall, like from some of your previous work, this is something that has been published. So you could try out the HydroML and test it on say our region. Because there's something I'd really like for the current research I'm doing is to just predict the performance based on attributes alone. And I need that for network optimization question. So I would love to try that.
Yeah, for now, the paper that I have and the code that is available is just for the HydroLSTM, so it's just to train locally. And now probably, I don't know, this semester I'm going to be publishing that the regional one where we're doing that together.
Okay, and are you doing that on like a kind of a department or university kind of supercomputing cluster, or are you just doing that locally? Like,
This
do you have a beefy GPU, or what do you do?
This is something very interesting that I have never mentioned that probably, in fact, I should stop that recording. But really, this is something interesting about HydroLSTM that is it runs much faster than LSTM. And there is a reason for that, because HydroLSTM is kind of deleting this kind of internal loop that you have, because for LSTM you have to go to, I don't know, go 1 year in the past, process all this information, and then do the prediction for this day, and then you have to do the same for the next time step. And with HydroLSTM, we are not doing that. We are kind of tracking the state, and we are just updating one time. So in fact, all the experiment that I did in the first part, just training locally, I did just using a computer, the CPU.
Wow.
I don't need a GPU. Of course, if I can parallelize that to do it, I'm going to do it even faster.
Oh, great! Yeah,
But comparing with a LSTM, it should be this way. In fact, something that I should do in some moment is that you can see here that even for the regional one, this should be faster. I don't have the architecture because I have to change my code. Because really what I'm doing now is kind of the more dumb way to do it, because I'm training in a CPU, training kind of catchment by catchment. But when I finish to train one, I go to the other one, and then I go to the other one. So this is taking a lot of time. But given that these trains are all independent, they could go inside of the GPU, and this way is going to be super fast. But I don't have the code to do it in this way. So I have to change the code, change the kind of architecture, how we are processing the data. But in general, this is my feeling that HydroLSTM, even the regional HydroLSTM, should be faster to train than LSTM.
I'm glad I asked. That was great. Thank you.
Luis, do you have the curve of performance showing the drop-off from individual train to regional trained?
I don't think so. I don't have it here. No, I don't have it here, sorry.
You have the tree though.
Yeah, this is the best decision tree.
So the first cut is the elevation, then slope, and then elevation again. Then GVF is some vegetation fraction.
Yes.
Green vegetation fraction, and that cluster ends. So far we got slope, elevation, and green vegetation fraction. And then you've got soil conductivity, mean precipitation twice, and mean potential evaporation. And that's where you got it?
Yes.
So the bottom, so the bottom one is not included. The bottom.
Yeah, because the tree can go deeper. So this is what mean the other one.
So elevation, slope, green vegetation fraction, soil hydraulic conductivity, precipitation, and potential evaporation. So those are your 1, 2, 3, 4, 5, 6 variables are being used. Yeah. And some of them are being reused. Okay.
Yeah, and here we can see immediately that the first one, the first split is in elevation. And in fact, the next one, if you continue for the faults, we see that it's using again elevation. So really the only thing is creating a different region. That one is higher than the other one. So it's kind
So
of
8 and 9, 8 and 9 are based only on elevation, and
yes.
which clusters are those? Can we see which clusters are 8 and 9?
Yes, these are the clusters that are in the mountain region. This one.
Okay, so those only use elevation as their predictor variables. Okay, then let's go back. Then we add green vegetation fraction, and that's all of the others. And then that splits that. So green vegetation fraction soil conductivity ends up in 1. Green vegetation fraction precipitation ends up in another. So 0 and 1 is green vegetation fraction soil conductivity. 2 and 3 is green vegetation and precipitation. And 4 and 5 is green vegetation and precipitation again. Okay, so 2, 3, 4, 5. And then 6 and 7 are green vegetation fraction and potential evaporation. You know, it might be valuable to list those or put this together with the other plot, so that we know this cluster is determined by these variables, right? That could help. So 0 and 1 are where?
0 is kind of the plains, and 1 is Florida. In general, they're kind of flat areas.
Right. And those are based on soil and precipitation. Yeah. Sorry, just based on soil. Okay. So low elevation, low greenness fraction, low soil, low soil conductivity. You know, if you put that like that, it makes it so much easier to try to understand what's going on. Whereas the next one is low elevation, low greenness fraction, and low precipitation. And then you've got low elevation, low slope, low greenness fraction, low soil conductivity. And low elevation, low slope, low greenness fraction, low precipitation. Yeah, okay. That's kind of interesting. Cool.
Okay. Another question?
Yeah, sorry.
Uh,
Did you code your own random forest, or what did you use?
No, I was using a Skylar library.
Okay. Yeah.
Okay, very cool, Luis. Thank you.
Yeah, thank you.
Okay, Leela, we're already, what, 11:40. Wow, that was a lot of discussion. Leela, what's on for the agenda for next time? That's Alex?
Yes, it's next time. Yes.
And then after Alex is?
I think we are gonna be on a break because people are going to EGU.
Okay.
And then we have a
Yeah.
Young's presentation. Mhm.
Okay. Very cool.
Thank
Thanks for
you,
coming,
Luis.
guys. I'm learning so much by
Yeah,
these
that was great.
discussions.
Thank you.
This is really, yeah. All right,
Thank you.
guys.
Bye-bye. See you in
Bye.
3
Bye.
weeks. Bye.